Hi there and welcome to the periodic table part 2. This fits with Science 9, Matter and Chemical Change. When you're ready, let's get started. All right, so besides breaking the periodic table into our three groups we did last lesson, metals, nonmetals, and metalloids, we can actually further break it down into groups or families and periods. Now you're probably wondering, what is a group or a family? Great question, my friends. Well, a group or a family is vertical columns. So do the arrows going down? These are called the vertical columns. These are your groups and families. We have them all the way across. Now, the groups and families are numbered across the top of your periodic table. So as we go across, notice that number 18 is the last group or family. So we have 18 different columns. Now, there's some cool things about these that we're going to look at next because some of these groups actually have some very cool names and some cool features. So as we talk about groups and families, the features I'm talking about, the similar characteristics that are distinct to each group or family. So some of our groups have special names, kind of like group number 1 over here. So group number 1, as I've highlighted, is called the alkali metals. The alkali metals do include hydrogen, but for the reactivity purposes of water, hydrogen doesn't really readily react with water, but the rest of them do. Now, the alkali metals are the most reactive out of all the metals, and that's a really important thing. And they actually react most violently with water. So you might have seen on YouTube or places like that, people throwing some of these alkali metals into water, and you see kind of fizzing or like big kind of like mini explosions and things like that. But here's the kicker. The reactivity actually increases as you go down. So lithium and francium, when we compare them, lithium is the least reactive. So this is the least reactive, and francium is the most reactive. So if you were to take a chunk of lithium and throw it into some water, it would just kind of like fizz across the top. However, francium, if you toss it, boom, big explosion. Now you're probably wondering why that is. Well, as we move down the periodic table, the atoms get larger because you're increasing orbitals. Every period is a new orbital level. So what that means is, for example, if I was in the first period, I'd only have 1 ring of electrons. Second period has 2 rings. Third period, 3 rings. Fourth period, you guessed it, 4 rings. Fifth period, 5 rings. Sixth period, 6 rings, and as you guessed, it was a terrible circle. Seventh period, 7 rings. So we compare lithium. Lithium is quite small compared to francium, which is very, very large. This large size allows francium to want to lose an electron very easily because metals lose electrons. And we'll talk more about that in the lesson about the atom itself. But that's what's happening here. So the group number 2 are the alkali or alkaline earth metals. I'm not going to really talk much about them. Yeah, they are reactive, not nearly as reactive as group number 1, but they are. And just like group number 1, reactivity will also increase as you're working your way down. Our next we're going to kind of focus a little more on is the halogens. The halogens are the most reactive non-metals. So, but the cool thing here is their reactivity is opposite as the metals. So when we look here, my fluorine is actually my most reactive, whereas my acetine is my least reactive. So as we go down, the reactivity, it decreases. And this is also due to the size because fluorine is so much smaller than acetine over here. That means that it's trying to gain an electron. So if you remember back to our lessons, right? Metals lose electrons, non-metals gain electrons. Because the atom is so small, that pull of that electron towards the nucleus is very strong. That's why fluorine reacts very strongly. Whereas acetine's so huge that pull that electron is not nearly as strong because it's such a huge atom. It can't really keep track of all the electrons that are out there and things like that. And this is why when you look at reactivity, an alkali reacts very aggressively or violently with halogens because alkalis want to give up electrons like nobody's business, and halogens are like, give me electrons. Our next one to look at here is the noble gases. It's highlighted in pink here for you. And these are the least reactive. We call them inert. That's why they weren't discovered till later on. So they don't really do that much stuff. So they don't really do a lot of things. And so here's my wonderful noble gases. They're just kind of like hanging out. Now, that doesn't mean you can't force them into reactions, you can. Remember, helium is very small. You can't really force it to go and bond with different things. However, radon is a massive like element. So you can actually kind of like sneak some stuff in, like, hey, like, take a fluorine. And you can actually push some things in. And so scientists have actually been able to make compounds with these noble gases because they're so big. But as you probably guessed it, yeah, it's only going to be like xenon kind of thing is the main one here that they do reactions with. And it's just because the size is so big. Radon isn't as stable, so it's hard to make bonds with it. All right, so now looking at these boxes, there's actually some cool information here. So every periodic table I've shown so far hasn't had all these interesting things written there. And there's a reason for that because it's complicated, but also I want to go into more detail. Let's look at fluorine over here to start. So I'm going to blow it up like this. Here's some key features about the most important information about the fluorine box, or actually all boxes. So first things first, that little number in the top corner, it tells you the atomic number. The atomic number tells you how many protons. Every single element has a set number of protons. As you increase the protons or decrease the protons, you change the element. This is how it is. Over here is the element symbol. The symbols don't always match the name. That's just because of where it was discovered. So don't get stuck up on that. We then have the atomic mass. This is how much the actual atom or element itself weighs. This is a combination of the protons and the neutrons, because electrons are so tiny, they don't really have a mass to them. But the atomic mass is the protons plus the neutrons. The element name is written here. The element name is typically, if it's written in a sentence, if it's not the first, it'll be lowercase or uppercase. But notice the element symbol is always an uppercase to start with. That's a really, really important thing. And then over here, the ion charge, if there is one. So for example, with noble gases are inert, so there is no ion charge. The ion charge tells you if the electrons are gained or lost. Because this ion charge here is negative, it's telling me that it's gaining electrons. And this makes sense because our non-metals gain electrons. Okay, let's practice this. So first question is, how many protons are in this element over here? I'm hoping you looked right here, and it's 26 protons. How about what is the atomic mass? Look at the numbers over here. What is the atomic mass? I'm hoping you saw this number down here, and you remember that's the protons plus the neutrons. And finally, what is the common ion charge? Ooh, ion charge. So the ion charges, my friends, are right here. The common ion charge is the top one. Notice that it's a positive number. It's positive because iron is a metal, which means it's losing electrons. And we'll talk more about this in the next lesson, about losing and gaining electrons. All right, let's recap, my friends. So groups are in vertical columns, right? They go up and down. Over here, we have the red, which is group 1. That's your alkali metals. Group 2 is your alkaline earth metals. Group number 17 over here is your halogens, and group number 18 is your noble gases. These elements here, so 13, 14, 15, and 16, are just named after the first element in them. So it's be like boron, and then it's going to be carbon group, and then it's the nitrogen group, and then it's the oxygen group. I know, very creative. You're welcome. All right, and then periods are the horizontal rows. It means they go across this way. And we have less rows than we do columns. And remember, if the elements are in the same column, they react similar. If they're in the same row, they're similar size. Thanks for listening. Have a scientific day, I should say.